All right, here's another video, and the two I can statements for this one are I can compare endergonic and exergonic reactions, and I can contrast endergonic and exergonic reactions. So they are both chemical reactions or types of chemical reactions. They both are looking at energy transfer. And that is where I'm going to stop with the both for now because we have a whole lot more differences and I don't want to run out of time. All right, so endergonic are going to be your processes where you are building something up, making more muscle, making more bone. And you may remember that that is anabolic. Okay, so those are your anabolic reactions. What you're going to see with this is you're going to see two monomers or 1,400 monomers or whatever, I'm just not going to draw that many, come together to make a polymer. Okay, so you're seeing bonds being formed, and since bonds are being formed, you're having to put energy in because you have to put energy in to form a bond. Okay, this is not going to be spontaneous because you do have to have that energy input. So it's going to need somehow to have energy in there. The free energy, or what you may have learned in chemistry, Gibbs free energy, or delta G, is going to be, that should be energy, is going to be positive, which means you have to add energy. All right. You are also, if you look back up here, you are increasing in complexity. So increasing in complexity because your product is more complex than your reactants. And you are decreasing in disorder because your reactants can go in different directions, but once you attach them all together, they can now only go in one direction. So you're decreasing the amount of chaos that's happening here. As far as an energy graph, what you're going to see with this is you're going to see your reactants down here are going to have a lower energy than your products. You are going to have a certain amount of energy that you're going to need to add to get the product or the reaction going. That is going to be your activation energy, so EA. And the difference in energy from your reactants to your products is that free energy, that delta G. And so you can see it's going up because it is positive. So your products have more energy than reactants. So this again goes back to you had to add energy in, because if you had, let's say, I don't know, 100 calories here and 200 here, then you had to add that energy to get to that 200. Exergonic is basically all the opposite. You're breaking down. It is catabolic. Okay, so you're going to start with a polymer and you're going to break it down into two monomers. It's going to release energy, so energy is going to come out. It is spontaneous. Now it does take a little bit of energy to get started, that activation energy, but overall it's spontaneous. The free energy, or delta G, is negative. You are going to be decreasing complexity because you're going from a very complex polymer to simple monomers, and you're going to be increasing disorder. Okay, again, this guy can go in one direction, but once you break it into its different parts, they can go in multiple directions. The energy graph for this one, you're going to see a little bit of a rise and then a fall. So here's your products, here's your reactants. That is your activation energy. And this is your delta G, and since it's going down, that's why it's negative. So in this case, your reactants have more energy than your products. And that is how you compare and contrast, there we go, your endergonic and exergonic reactions. I hope that helps. If you have questions, let me know.